All right, so let me first summarize the stuff we talked about in the previous lecture. So we talked about what we call the interaction of light and matter. And so I have a bunch of points here on the essentials of what we want to have. The idea is that in an atom, protons and electrons are attracted to each other. So the electron, being much less massive, will be sort of in an orbit about that nucleus where the protons are. But the electron is not free to be wherever it wants to be. All right, so anyway, the electrons are restricted to particular distances and energy in the atom. And each atom has its own unique set of orbital levels, okay, which we sort of call the fingerprint of the atom. The pattern of levels corresponds to a pattern of absorption and emission lines. And that's how we are able to identify the atoms. Now, when the electrons in these atoms absorb photons, they move to higher levels, and that shows up as these dark lines in the spectrum of a star, for example. So in this picture, we are looking at 3 lines that correspond to absorption in the hydrogen atom. Okay, so we know that that particular star contains hydrogen because of those pattern of lines are there. When the electrons jump down to lower levels, they emit photons. They release the energy that they had. And we can see those as emission lines. Now, what's below the colorful spectra that you see here is digital spectra. And the digital spectra is usually how we get our data. So in digital spectra, you get information about intensity in addition to what's going on in individual wavelengths. So because the color that's up here at the top doesn't really give you an indication of how intense the light is. But you can see from the spectra here, the digital one, that the lower wavelength side, the blue side, is at a much higher intensity. And the absorption lines show up as these big spikes, these big drops in the intensity. And that's what they are. They're just places where there is very little light at those wavelengths because it's being absorbed by the atoms in the atmosphere. The shape, by the way, of the spectrum there tells us a lot about the temperature of the star, which we're going to talk about today. Okay. Now, before I get into that, I want to kind of continue talking about some physical laws and principles that we're going to use. And since we're talking about the ideas of light and temperature, it's sort of appropriate to talk about that now. So we talked before about using Newton's laws and gravity as a means, sort of as a tool to analyze the behavior of things we see in space. There's a lot of other tools we have. One of those things is energy. When we look at systems, we want to characterize the energy of those systems. And that can also tell us a lot about what's going on there. So there's different types of energy that we'll talk about. There's kinetic energy, which is energy due to the fact that objects are moving. So if an object has particular speed to it, we can talk about its kinetic energy. If objects move very, very fast, then they have the ability to impart a lot of energy to other things. So that's important. Light is obviously a type of energy because we talked about photons having energy. We call that radiative energy. So sunlight, light bulbs, the incandescent lights in this room, that's all radiative energy. And then we have lots of different types of what we call stored or potential energy. Gravity is a type of potential energy. If you have an object, for example, at a height, at a particular height, it has the potential to fall and speed up as it falls, and that is a type of stored energy because that can be released. Food is a type of stored energy, chemical energy. You eat food, that contains energy, that makes the body work. There's lots of various kinds of the stored potential energy we talk about. Obviously, gravitational energy is going to be really important. So when it comes to gravitational energy, there's a few factors that matter. I mean, the easiest way to think about this is if you have an object that can fall from a certain height, what are the factors that are going to determine how much energy is released in there? Mass is obviously an important factor. Okay, if you have a small rock that falls from a meter, that's very different than having a large boulder fall from a meter. Okay, so mass is an important factor in that, and the distance that the object falls is a more important factor. Okay, so objects at a very high, at a particular height, if it's very high, have the potential to release a lot more energy. So when something falls, the more it falls, the faster it can go, and so we can characterize potential energy like that. Now, one of the ways that we will talk about potential energy, I'll just give you one quick example, is star formation will be a very important topic when it comes to gravitational energy. So in this example here, there's actually a couple things going on in this example. We're going to see later on that stars are born from really large interstellar clouds. So there's clouds all throughout space. And what happens to these clouds is something triggers them to compress. Something compresses them and it triggers them to collapse. And what's happening there is this big cloud will start to shrink. As it shrinks, you think about all of the molecules of that cloud falling toward the center of the cloud. And when it does that, it's releasing gravitational energy. The fact that you have all this mass here, all separated some distance, means there's a lot of gravitational potential energy. And as all those molecules fall towards the center, they are going to be releasing that gravitational energy. Okay? And it goes into various forms. Okay? One of the main ways it happens is by releasing gravitational energy and turning it into kinetic energy. All those molecules are going to start to travel very fast as they fall towards the center. As we've talked about when it comes to angular momentum, if this cloud has any kind of motion to it, as it shrinks in size, it's going to start to spin, and it can spin very rapidly. That's another type of kinetic energy. So that kinetic energy comes from the fact that there's all this gravitational energy. And obviously the cloud's going to heat up a lot as well. So that kinetic energy eventually gets converted to thermal energy. Okay, so understanding how the gravitational energy gets converted to kinetic, gets converted to thermal, is going to be a really important theme when we talk about how stars are born. Okay, and so that will be something we'll be talking about a bit. Now, thermal energy relates specifically to this chapter, since we're talking about the ideas of light and energy, and thermal energy is a big part of that. Thermal energy is actually a type of kinetic energy. It's a way that we characterize the average, well, let's put it this way. Thermal energy is a way to characterize the sort of amount of kinetic energy that something has, which sounds very similar to temperature, but they actually have some distinctions. So let me be very clear about, let's define all these things. The first thing we want to talk about is the idea of what temperature is. Okay? Temperature is defined as the average kinetic energy of particles in a system. Okay, so what do I mean by that? Well, imagine I have two glasses of water. Okay, I have one glass that's cold, another glass that's very hot. Okay, when you touch those things, okay, you obviously can sense that one is colder, one is hotter, and one of the ways you primarily do that is the flow of energy. Okay, if you touch something that's cold, energy is being removed from your hand, going into the glass, and you feel that energy transfer. That we call that heat. And when you touch something that's hot, energy is flowing into your hand. Okay. Now, ultimately, what's going on at a really fundamental level is this. If you could somehow see the molecules of water in these glasses, what you'll see is that the higher temperature water, okay, the molecules in there are moving around much more rapidly. I mean, every molecule has some kind of random motion that goes along with it. Something that's colder simply has less of that bouncing around motion, and something that's hotter has a lot more of that. So when you're touching something that's hot, you're sensing that. You're sensing all those little micro collisions that are taking place, and that's how you know it's hot. Okay, so that's what we mean by temperature specifically. The idea of thermal energy, though, is looking not just at temperature, but looking at sort of the overall, like the collective kinetic energy that exists in the system. Not just an average, but like an overall collective amount. And one way, I'll go back to that. One way to illustrate this real nicely is the example here. We have an oven that's heated to 400 degrees Fahrenheit, and we have a pot of boiling water that's heated to boiling, so 212 Fahrenheit. Okay. Now, if you stick your hand in that oven, let's say for a few seconds, you're probably going to be fine, right? There's really no harm in sticking your hand in an oven for a matter of a few seconds. But you stick your hand in that pot of boiling water for a few seconds, you're going to the hospital. Mm-hmm. The reason why is because even though that oven is much hotter, so we would say its temperature is much higher, the difference is the amount of thermal energy that's involved. The pot of boiling water has far more thermal energy. The collective kinetic energy is much greater. Okay, and so for the oven, when you stick your hand in the oven, the air molecules are colliding with your hand, and they're colliding with your hand quite violently, but not very often. Okay, so the average collision that's taking place with an air molecule in your hand is of pretty high energy, but it doesn't happen much. The pot of boiling water, on the other hand, the average collision with a water molecule in your hand is of a lower energy, but it's happening at a far greater rate. Far, far greater rate. And so after just a matter of a few seconds, you've had enough smaller energy collisions to add up to much larger damage. Okay, and so you end up, the collisions are basically destroying the molecular bonds of your cells, basically killing your cells. And that's what a burn ultimately is. And so thermal energy involves the concepts of temperature and density. Okay, density is an important factor. So when something is very dense, it has a lot more thermal energy with it. Okay. Now, just to touch on the ideas of temperature again. Now, because we live in America here, most of us are used to the Fahrenheit scale, which is what we've adopted here in America, and it's honestly, it's a rather odd scale. The basis for the scale, it's kind of sounding kind of weird, but the basis for the scale was water freezes at 32 and water boils at 212, and the difference between those two numbers is 180. And the existence of the Fahrenheit scale was to make exactly 100 divisions of 1.8 degrees apiece. And that's how the Fahrenheit scale ended up being created, which is odd though, because the numbers are really kind of strange. Now, most of the world uses the Celsius scale, which has a similar thing. It uses degrees as well, but the way it works is 0 is the basis for the scale, and so 0 is freezing and 100 is boiling, and so you have exactly 100 divisions between freezing and boiling. And so most of the world uses Celsius. However, in the sciences we use Kelvin. And Kelvin is simply a recognition. It's very similar to Celsius, except there's a different 0 point. That's it. The 0 point is the lowest temperature that you can have. So in the Celsius scale, the 0 point is water freezing. In Kelvin, the 0 point is we call absolute zero, the coldest temperature you could possibly achieve. And that's a temperature where the particles in a system don't move at all. There's no random motions at all. They all stop, which is almost impossible to do, but that's a standard. And so when you do that, water freezes at 273 and boils at 373. Room temperature is around 300 Kelvin. That would be what we would say room temperature is. That's a little high, but no, that's room temperature. Most room temperature is about 300. Now, most Kelvin temperatures we talk about are actually really high. We're talking about temperatures of stars, for example. That's really high. And what I can tell you is the best way to sort of imagine what we're talking about in terms of Fahrenheit is this. When the temperatures are high, like in the thousands, you can double a Kelvin temperature, and you roughly will get what the Fahrenheit temperature is. Okay. So, for example, in Kelvin, the temperature of the sun is around 5,500. Okay, 5,500 Kelvin. If you double that, you get something that's around 11,000. The sun's temperature is about, it's a little less than that. It's closer to 10,000. But if you double a Kelvin temperature, you get pretty close to a Fahrenheit temperature. But that only really applies if you have really high temperatures, like in the thousands. So we're going to be using Kelvin quickly. Okay. Now, I want to say one more thing about the idea of thermal energy and temperature, because there's one thing kind of missing from this that I want to make sure it's not confused. We have temperature, we have thermal energy, and we have this other idea called heat. Okay, and what heat is the flow of thermal energy. Okay. It's how energy goes from one place to another place. And that varies with different substances. Okay, so when I touch the board here, okay, it feels cool to me. Okay. What's happening is a heat transfer. Okay, my hand's warmer than the board, so heat's flowing out of my hand into the board. Now this wall that's right next to the board here, this is at pretty much the exact same temperature, because we're all in the room here. When I touch it, it doesn't feel as cold. Okay, and it's because the wall has a different ability to conduct heat. Heat doesn't flow as easily. And so that's different from these ideas, but it is closely related to thermal energy. It's simply the flow of that thermal energy. And in some cases, this can be really extreme. Yeah, actually, to illustrate, another good thing that that's illustrated in that point there is that we don't sense temperature. We ultimately don't sense temperature. We ultimately sense heat. Okay, if something is very hot or very cold, the way you know that is because of the amount of heat that's transferred. Most common substances transfer heat at the same rate, basically. There's some differences. Some things are significantly, better at conducting heat or worse, but for the most part, most things do it pretty similarly. And so when you touch something that's hot, you're really detecting the heat flow, not really the temperature itself, because you can't touch an object and know. It's 112 degrees or something like that. You don't know. You just know it's hot. Okay, unless you somehow have calibrated in your mind how heat flow transfers to temperature, you can't really tell. And in some cases, your brain just loses its mind. It can't tell. I mean, I remember when I was a kid and I had to go to swimming lessons, the ground would be so hot it actually felt cold. And that's just because my brain's confused. Okay, there's another thing you can do. Apparently, there's this experiment you can do where you can take, I saw this in a Vsauce video, but you take hot dogs and you take a bunch of hot dogs that are cold and a bunch of hot dogs that are hot, and you sort of stagger them. So you have a hot dog, and a cold one, and a hot one, and a cold one, and you put them in a row, then you stick your arm on it. And when you do that, it just messes with your brain. You can't tell if it's hot or cold, and people just like move their hands, think they're burning, but it's really not. They're really kind of warm or something. Anyway, it's a neat little thing, but I'm not sure. It was in this Vsauce video that he did, and it was kind of neat. But yeah, so that is your brain just being like, I don't know what's going on here. And so it just can't process what's going on in terms of it being hot and cold at the same time. Okay, anything else? Great. All right, so let's talk a bit more about this thermal energy. Now, what we talked about at the end of last lecture was one of the ways that you can excite atoms. And one of the ways you can do that is by light hidden atoms. And certain wavelengths of light will be absorbed and it'll kick electrons to higher levels. That's one of the ways you can interact light and matter together. There are other ways that you can excite atoms, and it's not by photon absorption, it's by collisions. Okay? When two molecules bounce into each other, you can also transfer energy that way. Okay? Same mechanism, actually. You can have two molecules or two atoms collide, and that collision is an energy transfer. And it could kick electrons up to higher levels. That's another way you can do it. And this is a very common phenomenon. Okay? I mean, everything has a temperature to it. And that means every substance has these random motions that are occurring in the molecules, and that means there's a lot of bouncing around that occurs on a molecular level. And so things are constantly colliding with each other. And that means if things are constantly colliding, that means you're bound to be kicking electrons up to higher levels, which eventually have to kick back down, and that eventually releases light. Okay? And that's true. Anything that is hot and relatively dense has these little collisions taking place on a microscopic level. And the result of that is to produce something that we call a thermal radiation spectrum. Okay. And now the exact way that this happens, the exact mechanism by which you have an object that's hot and dense and the molecules are colliding with each other, kicking electrons to higher levels and all that and releasing light, is actually pretty complicated. In fact, it's so complicated that an entire branch of physics had to be invented to explain the phenomenon, and that branch of physics is called quantum mechanics. That was the original intention of quantum mechanics, was to explain ultimately the question as to why do objects glow when they're hot. Okay, 100 years ago, let's say about 100 years ago, we really couldn't properly answer that question. Why do objects glow when they're hot? Because we didn't have a very good understanding of atoms and how atoms interact, and ultimately the reason why anything glows when it's hot is because there's something going on a molecular level. But so we don't need to be concerned about the mechanism. All you need to know is this. Any object that has a temperature that can be characterized with a temperature and is dense. So that means any solid, any liquid, or even a really dense gas. Okay? And it has a temperature. It doesn't matter if it's really cold or it's actually hot. It will produce a thermal radiation spectrum. It will release light. Okay? And this thermal radiation spectrum is also sometimes referred to as a continuous emission spectrum. It emits light, but not at certain wavelengths like we talked about for photon absorption and emission. It emits light at every wavelength, every single wavelength. Okay? And the way that that looks is illustrated in this picture here. Now, on the right-hand side, we have 3 different examples of extremely hot objects. So the one at the bottom here is at 5,000 Kelvin. The middle one's 6,000, and the top one's 7,000 Kelvin. Okay, those are common temperatures you'd have for stars. These are not temperatures you would experience on Earth at all. Okay, if you experience these temperatures, you're going to be dead. Okay, these are way too hot. I mean, that 5,000 Kelvin temperature, that's around 9,000 Fahrenheit. Okay, so that's extremely hot. But when objects are this hot, these graphs here are illustrating how these objects emit light because they're so hot. Okay, so if I look at the middle one here, the 6,000 Kelvin, by the way, this is very close to the temperature of the sun. Okay, so we have wavelength on the horizontal axis and we have intensity. Okay, so what we see here is that there is light being emitted at every wavelength. Not equally. Okay, there's more visible light being emitted than ultraviolet and infrared light. Okay, but it is light every wavelength, and that is true of every thermal radiation spectrum. It's light at every wavelength, but it varies depending on the temperature. So there's more of one type compared to another one. This particular object happens to have a peak around green light. The object actually doesn't look green, though, because you have sort of an even mixture of blue and red, and so it takes a very sort of whitish appearance. The one at the top is emitting a lot more blue light than anything else, and so the object will actually look blue because of that. And the one on the bottom would probably look kind of reddish in appearance. Right. Now, this is how objects look when they're extremely hot, but everything does this. Okay, I mean, this desk here, this desk produces a thermal radiation spectrum. It's just not hot enough to glow. You can't see the light that's being emitted from this. Okay. Now, you've seen this to some extent. I mean, you see some of this. For example, if you have an electric stove, right? You turn the electric stove all the way up, what happens to those coils? What do? They light up. They start to glow, kind of orangish, right? That's due to this stuff here. Now, they don't get anywhere near thousands of degrees. They probably get in the upper hundreds of degrees, but it is hot enough that the thermal radiation spectrum starts to show. You get that glow. Okay, it's the same kind of glow you would expect to see from a fire. Okay, so like if you have like a campfire and you see those logs glowing, it's the same color. It's the same phenomenon. It's a thermal radiation spectrum. So you primarily see reddish colors from this. Now, it's true that objects can be hot and look blue, but trust me, you have never ever seen an object on Earth that is so hot that it's blue. Because if you did, you wouldn't be allowed to tell anybody about it. Okay, again, a blue object, that blue object there is around 13,000 Fahrenheit. And at 13,000 Fahrenheit, nothing can live. Okay, so when you do see things that are blue, that glow blue, you are seeing a chemical reaction as opposed to a thermal radiation spectrum. Okay, so that example I gave for the electric stove, if you think about a gas stoves has a blue flame. That's not related to this for a couple of reasons. One, this requires a hot, dense object. Okay, the flame from the gas stove is not dense, so this couldn't be taking place. What's happening is there's a chemical reaction, the natural gas is oxidizing, and that produces a blue emission line. So that's a line emission. That's actually an emission line. That's the stuff we talked about last class. That's not related to this. If you ever see an object glow because it's hot, it's always red. Okay, it's always red. When you look at the stars in the sky, if a star looks blue, then it actually is blue because of this. That's probably the only way you've ever really seen this is a blue color because the object's so hot. But anyway. And so obviously this is going to be a very important topic because every star is extremely hot. And every star initially emits their light in this fashion. Okay? And so understanding this obviously is going to be a big part of understanding stars. Okay. So, any initial questions about this stuff? Yes, Steve.
Can we relate volcanoes?
Volcano? Absolutely. The lava that comes out of that is thousands of degrees. The red color that you see is absolutely due to this effect. Yep, absolutely. Okay. Now, I will say one thing about that, though. I mean, the lava that comes out is not at 5,000 Kelvin or at 9,000 Fahrenheit. Even though this looks red, what happens is when you have objects that are cooler, okay, well, let me point out one thing here. Notice something about these peaks, okay, in these different objects here. And the peak is important because that is the wavelength of light that's being primarily emitted by the object, and that will determine the kind of color that it has. Okay, so the object down here will look red because there's more red light coming out than any other color, so it will look that way. The one in the middle here doesn't really look green. You have an even amount of colors almost here. It's almost equal red and blue. You do have a bit more of green, but for the most part, it's going to look like a yellowish, whitish color because when you just mix all the colors evenly, you just get white. And the one at the top, though, is clearly a lot more blue. Now, what happens, though, is if you change the temperature of these objects, you see how the peak changes. As the object heats up, the peak shifts over to the left side, to the shorter end of the spectrum, the blue end, we say. This one down here is in the red end. If we were to lower the temperature even more, the peak moves further to the right and actually can move into the infrared. Okay, but we only see visual part of the spectrum. And if you look on the left side here, there's a slope to these curves. We are always having more red light being emitted than blue light. So when you have the object cooler, it will always look red, okay, because of this slope that exists. So most things that you see that are red, like example for a volcano, campfire, electric stove, they're not thousands of degrees, but they're hot enough that the red part is starting to show a bit. I mean, most things, on Earth are emitted in the infrared. Okay, all our bodies are emitted in the infrared. Okay, the desks are emitted in the infrared. Have you ever had a chance to see things in an infrared camera? Okay, like when you go to Griffith Observatory, they got an infrared camera. As soon as you walk in, go to the left, with the Tesla coil, they got this infrared camera there, and you see people glow. Okay, because it's picking up this stuff. That glow is from thermal radiation spectrum. All right, so I want to talk about a couple properties here. That one I kind of already hinted at. But when it comes to understanding this stuff, we have two we call thermal radiation laws. There's two things that I really want to know about the objects that we're looking at here. Okay. So the first one is called the Stefan-Boltzmann law. The Stefan-Boltzmann law is a really simple statement. It says an object that's hotter will be brighter. Okay. So conceptually, it's real simple. Hotter objects are brighter objects, or we say more luminous. Okay. But there's an equation that goes with it. And the equation is that the amount of power, so the amount of energy being released per second from the object, the emitted power, which is just given in watts per square meter, is equal to sigma temperature to the fourth power. Now, sigma is a constant. It's equal to that number that I have there, 5.7 times 10 to the minus 8. It's just a constant. And the T is temperature in Kelvin. Okay, so if you were to plug in the temperature of an object in Kelvin, what this gives you is watts per square meter. How much energy is being released by the object, how many watts per square meter of the object. Okay, so this is a way that we characterize how much energy is being released by the object. Okay, that's one of the laws. You could see that in the pictures over here in this way. As the objects get hotter, what happens is the intensity goes up. Okay, so if we look at the 6,000 Kelvin object compared to the 5,000 Kelvin object, what we see is that at every wavelength, okay, there is more light being emitted. Okay, when you go to the 7,001, there's even more light being emitted at every wavelength. So the intensity goes up. Okay, we expect the objects to be brighter and brighter. And that's what Stefan-Boltzmann law says. But it's actually an equation, and you can plug a number into it, which I'll do in a moment here. All right, the other law is called Wiens Law. And what it says is that the peak in these thermal radiation curves, okay, the peak of the thermal radiation curve, will shift towards shorter wavelengths as the temperature goes up. Okay. And there's an equation, and the equation is lambda max, which is the wavelength of peak intensity, okay, is approximately 2.9 million nanometers divided by temperature. Okay, now your book actually uses 3 million. I should change it on my slide, but I haven't yet. But anyway, your book uses 3 million, not 2.9 million, which is fine. So the idea is that if you plug in a temperature in Kelvin here, what this equation gives you, it tells you the wavelength that's being primarily emitted by the object. Okay, that's what it's doing here. And again, you can see that in the pictures. Okay. Wiens law is illustrated in the pictures. Okay. In this spectrum here, the bottom, the 5,000 Kelvin one, okay, we have primarily orangish red light being emitted. Okay. As the object heats up, this wavelength shifts to the left, to shorter wavelengths. So as we heat it up, now it's greenish light, that's primarily emitted. We go to 7,000 Kelvin, it's bluish light. Okay, if I have a hotter object, it would shift even further, it would go into the ultraviolet actually. So that's Wiens law illustrated. Okay, the wavelength shifts to the left. Okay, and that's what the two laws are. You heat the object up, the intensity goes up, and the wavelength shifts to lower wavelengths. Those are the two. Okay, the nice thing about Wiens law is it allows you to take an observation. Okay, say we have an object, we don't even know what its temperature is. But say we've taken its spectrum and we can see where the peak is. We can see the wavelength that's being primarily emitted by that object. Wiens law allows you to plug that in and get a temperature out of it. And this is one of the ways we can determine how hot stars are. We look at its spectrum, we determine where the peak wavelength is, we get a temperature out of it. So that's Wiens law. Okay, so let me give you some examples of this, right? Some examples of this. All right. So we want to know what the emitted power per square meter and the wavelength of peak intensity is for a 2,000 Kelvin object. Okay, so this would be an object that would be around, I don't know, 3,600 Fahrenheit or something like that. So what we do is we take that temperature, we plug it into the two equations. So for the Stefan-Boltzmann law, okay, it's sigma, which is always this number here, 5.7 times 10 to the minus 8. Times the temperature to the fourth power. So it's 2,000 to the fourth power. So you plug it all into your calculator, and that would give us 9.1 times 10 to the 5 watts per square meter. Almost 1,000,000 watts for every square meter of surface. Okay, so that's telling us the relative, well, it's telling us what the intensity of light is, how luminous the object is. Okay, so for Wiens law, do the same thing. We plug in the temperature. So we have 2.9 million divided by 2,000. The number we get out of that is always going to be in nanometers. Okay, this is 1,450 nanometers. So you got to know what kind of light that is. Okay, if you remember, visible light is 400 to 700 nanometers. Okay, when you get to 700, that's red. And if you go beyond that, you go into the infrared. This is infrared light. Okay, so this particular object that's 2,000 Kelvin has its peak in the infrared. It's primarily emitting infrared light. Okay, it would actually look red though, because as you go into the visual part of the spectrum, you get that slope that I talked about, the red slope. All right. So that's how we use these equations. Do you have any questions about that? Yes. The W, it stands for watts. So energy per second. Yes. It's the same thing that we talk about. We talk about a 100-watt light bulb. except this particular object has the power of having, 10,100 watt light bulbs in a square meter of area. Pretty bright. All right. Are there any other questions about this? Okay. Do you know why I'm showing you these examples? Because I'm going to ask you to do it on the homework. You bet. All right. Both of these equations are going to rear their ugly head again more than one time in this class. Okay? This is really fundamental, important stuff in astronomy. Really important stuff. So we're going to be talking about it multiple times. This is the first time you're going to see it, but you will see it again. Okay? All right, so let me give you a variation of Wiens' law, because actually you could do two things with Wiens' law. So the original equation was lambda equals the 2.9 million over temperature. You can switch it around, and you can do the opposite. You can solve for the temperature. So what you can do is, say you find an object, right? Say you find an object, and you've taken its spectrum. You have no idea how hot it is, but you could see in its spectrum that it primarily emits ultraviolet light, and you discover that the peak is at 150 nanometers. So whatever means you do that, you find out that the peak's 150. You plug it into Wiens' law. So you rearrange the equation. You basically just swap the two variables here. And so we would put 2.9 million over 150 nanometers, and what we get out of that is 19,000. So that means the object must be 19,000 Kelvin if it's emitting primarily ultraviolet radiation at 150 nanometers. So that is the other way we use Wiens' law. In fact, this is the primary way we use Wiens' law. We don't know the temperature of objects in space, but if we can observe their wavelength, we can automatically determine what their surface temperature is. So that's why this is how it's primarily used. All right. Use 3 million. Use 3 million. Although when I have the homework question, I keep it open-ended. So put the numbers in, and I don't trust I don't trust Canvas to figure out your numbers. I just look at it myself. So as long as you didn't write it in a way that I can't understand. I mean, if you use either number, I would accept it, but you should use 3. Now there is examples in the book. They use 3. I don't know exactly where it is in the book. It's obviously somewhere in chapter 5, but you want to look at those examples. But if you follow the example I'm doing here, and you look at the examples in the book, whatever page they're on, then you'll find it. Where'd you get that book from? Okay. It's on page like 1 something, 114, 115 in that book. Yeah. I think it, no, next page. Yeah. Yeah, right there. Okay. Oh, they use 2. Yeah, well, because I switch books. You can use either one. Either one's fine. All right. I'm going to move on.
Did you round it?
Probably. 29 over 15 doesn't come out nicely. I must have rounded it, yeah. Oh, yeah. I'm not going to care about you rounding things correctly. Actually, that's not true. Never mind. You should round reasonably, I guess. Yeah. Like on that, you had a question about Kepler's laws, and I had you work out some period or something. It kind of to like 22.6, and I was supposed to round to 23. But whatever. All right. Anyway, are you sure? You got any other questions? All right. Well, good luck in the homework. It's not that bad. It's not that bad, but just follow the example. All right, so this is a great picture because this is what happens to our sun. This is our sun here, okay? There are 3 things in this picture, okay? You have this dark, well, this line, okay, here, this thin line. That thin line, what's labeled here, it says ideal black body. Ideal black body, what they mean is the thermal radiation spectrum. Black body is another name for it. Okay. Now that line, okay, is the light that's being emitted by the surface of the sun, what we call the surface, the photosphere of the sun. That is the level of light and the type of light that's being emitted from the surface. Okay. So it says ideal because that's what like the equation would tell us the light looks like. We can't see this light because you'd have to be on the surface to see this light. The problem we have is we have to look through the atmosphere of the sun to see that light. Now, when that light passes through the atmosphere and gets out into space, it takes on the yellow color that you see here. Okay? And as you can see, the yellow color is pretty close to what the ideal black body is, but it's not exactly the same because as the light passes through the atmosphere, it encounters all kinds of atoms that do absorptions and re-emissions and things like that. So there's some differences. For example, if you look on the very far left here in the ultraviolet, the intensity of light is less than it is from the surface. There's a lot of absorption that takes place there. You'll notice in the visual part of the spectrum that the level of light is actually higher than what was emitted from the surface. A lot of the ultraviolet light that was absorbed got re-emitted in the visual part of the spectrum. So the sun's actually a little bit brighter once the light gets out of the atmosphere than it was on the surface. And then as you go through the infrared, there's a little bit of difference. So you can see the level of light's a little bit lower than we expected it to be. But for the most part, it takes on that shape. Now, when that light actually gets to the Earth and then goes through our atmosphere and gets to the ground, that's the red. Okay? And so the light is significantly affected by our atmosphere. Okay? In the visual part of the spectrum, it's just an overall diminishing factor. So it takes on a similar shape, but it's a much lower intensity. In the infrared, you've got a lot going on here. The spectrum is chopped up quite a bit. It's due to water, CO2, CO as well. You can have methane absorbing stuff here. And of course, you see the ultraviolet gets wiped out pretty good, which is good. We don't want a lot of ultraviolet getting in. So a lot of that gets diminished significantly. And there's a small portion here, which is why you have to wear sunscreen. But a lot of the ultraviolet does not get through. And a lot of the the water and the CO2 that wipes out things here, a cause for greenhouse effect and things like that, and global warming and all that stuff. That stuff, not only does that stuff absorb light as it comes in, but it absorbs it as it comes out, which is the whole greenhouse effect. The ground heats up and then re-radiates stuff in the infrared. It's absorbed by those things. All right, so this is an example of one particular star, our star, and how we see the thermal radiation spectrum. Okay, there's what happens at the surface, which is like the perfect ideal spectrum. Then it passes through the atmosphere, it changes. Then it passes through our atmosphere, and it changes even more. Okay, and we have means to we know exactly how this light is affected by our atmosphere. So we can extract out that information and get the yellow part. We don't have to actually be in space to see that yellow part. We actually can correct the spectrum on Earth. One thing we can't get is we can't get that ideal black body because that would require us to be in the atmosphere of the sun to actually see what light that is. But every single star has a picture like this. Every single star has an initial black body curve that corresponds to its temperature. It has the yellow part, that's once it gets through the atmosphere of the star, and then there's the red part that gets through our atmosphere. Every star has a picture like this. Okay. And one of the things we do with this is we look for those peaks. Those peaks, we use Wiens' Law, we figure out how hot it is. All right, any questions about this? All right. Oh, all right. Got some astronomy poetry here. Star A is red and star B is blue. Assume they're basically the same size. Which one has a higher surface temperature? They're saying B. It is B. Great. So when it comes to colors of things in space, that's the general assumption you can make now. If something's blue, you can, for the most part, assume that it's hot. And if something's red, it's cooler. Okay. Well, yeah, actually. So, commonly we associate blue with cold. because that's kind of true. So when something's cold, I wouldn't say it looks blue necessarily. I mean, things kind of look blue because of the way water looks, but yeah, in space, blue means really hot, and red means relatively cool. Obviously red's still pretty darn hot, so. All right, good. All right, another question for you here. Star A is red and star B is blue. Assume they're basically the same size. And now we also want to say that they're located the same distance from the Earth. Which star would have a larger apparent magnitude? So think about this real hard first before you answer. Think about this, what you think would be. Which star has a larger apparent magnitude? The answer is A, and you're all saying A. What is going on? Why are you saying A? I want you to say A, but I didn't expect you to say A. Demon, what's up?
I was going to say because it's longer, the blue was shorter when we were talking about the radio and the light red was longer. That's why I thought it has a
Well, maybe.
Larger magnitude.
Somebody else explain to me. Why is the answer A? Because that's not normal unless you guys all conspired and want to trick me or something. Yeah, you're almost right there, but you're missing something there. Why? Somebody tell me why you chose A. I demand the answer. Sarah. Okay, that's right. What she said was that B would be brighter. B would be brighter, right? Because it's hotter. That's Stephan-Boltzmann law. And objects that are hotter are characterized by a lower magnitude. You all said that, right? That's what your logic was, right? Yeah? Okay. Well, I don't believe you, although I want to, because this is a very common misconception that I get in this class. Because what happens is, when I say larger apparent magnitude, that means fainter, an object that's not as bright. But most people forget that, but you didn't. So that's weird. That's okay though. Maybe I'm doing something different. You remember that?
Yeah, that's what you said. You said everybody makes that mistake.
Yeah, I did say that.
You're not going to remember next week.
But then when I say this, then you're like, oh, I forgot you told that story. I forgot you said that. But you guys remembered. Aww.
It's also the other reason that red light stays brighter for a longer period of time than blue light does over time.
Wait, say that again?
Red light usually stays brighter over a longer period of time than blue light.
Well, okay, so in this case here, the stars have this like constant power source. So they're always going to remain at this color or temperature. So you're talking about something that's like cooling off or something like that. This is different because we're talking about maintaining that same temperature. So if we're talking about all things equal here, same distance, same size, the colors are purely due to temperatures which are constant. They're not going to change. So blue being brighter means a smaller magnitude. Okay, good. I'm just going to stop being shocked by you guys answering the question correctly. Okay, that's good. Fantastic. All right. So here's Orion. And, Orion, there's these two a lot of stars in Orion are very bright. And the two brightest stars in Orion are Betelgeuse and Rigel. Okay, Rigel's in the bottom here, bottom right. Betelgeuse is upper left here. And Betelgeuse is a predominantly red-ish looking star, and Rigel is a very predominantly blue-looking star. And now you know why. Rigel is a significantly hotter object, okay, than Betelgeuse. Betelgeuse is a temperature around 3,000 Kelvin, where Rigel is a temperature that's around 18,000 Kelvin or so. It's much, much hotter. Now, let me ask you this, though, Because while you understand some things about temperature, let me give you a little conundrum here, right? So we've established that Rigel is a hotter object than Betelgeuse, right? But get this. They're both in Orion, and they're both approximately the same distance from us. Not exactly, but close enough. What's strange about these two stars is that they're almost identical in brightness. They're almost identical in brightness. Betelgeuse and Rigel look very similar to each other. In fact, when I talked about Hipparchus and all that classification stuff, we put them in the same rank. However, traditionally people always associated Betelgeuse being the more prominent star just because it's red. It stands out more. But anyway, they're about the same brightness. They're about the same distance. Okay, we know Rigel's much hotter. So what do you think is going on here? Why would these objects be similar in brightness if one is much hotter than the other one? What do you think's going on here? Do you think, let me ask you more specifically here. What do you think's special about Betelgeuse that would make it appear to be the same brightness that Rigel is? It is larger in size. Okay. That's a good answer. That's right. Okay, I didn't expect that one either. All right, but yeah, that's good. Yeah, I mean that's what's going on. Betelgeuse happens to be huge, and it's cooler, right? But its surface area is enormous. So even though it's colder, I shouldn't use the word colder, cooler, because it's still like 3,000 Kelvin. It has all this extra area to emit light, and so it makes up for that lower luminosity by having this huge surface area to it. Rigel is probably like 3 times the size of the sun, where Betelgeuse is something like 500 times the size of the sun. Okay. No, not exactly that. This is a size argument. It's due to size completely. Betelgeuse is so huge. I mean, if you would put Betelgeuse in the solar system, you replace the sun with Betelgeuse, its surface goes all the way out to like Saturn. It's huge. And we'll get into this a little bit later in the class, but this is how we're able to figure out sizes for objects. We cannot see the size of these things. These are so far away, we cannot tell how big they are. The sizes of the stars you see in the image here is due to their brightness, not due to their actual size. But we can figure out how big they are based on what we were just talking about here. Okay, if you look at how they emit their light, how hot are they, how bright are they, you can actually infer their size. Yeah, Betelgeuse is huge. So, all right, great. Now, let me sort of summarize the stuff we've been talking about in the previous lecture and today. You could summarize all of these ideas that we're talking about for radiation in these laws here. They're called Kirchhoffs Laws of Radiation. There's 3 of them. And what they do is they basically describe all the situations where light and matter interact. Okay. And so I'm going to go through each one of these things. The order that I present them here may not be the same order the book has them. The order I put them in is just a more logical order. Now, the first law is on thermal radiation spectrum. Okay? Thermal radiation spectrum. What it says is that if you have a solid, liquid, or dense gas, so you have to have something that's relatively dense, okay, and can be characterized by temperature. Okay, so solid, liquid, or dense gas excited to emit light. All that means is it's dense, it's hot. Okay, not even hot, it just has a temperature. Right? It will emit light at all wavelengths and produce a thermal radiation spectrum or continuous radiation spectrum. So everything that's dense and has a temperature will release a rainbow of colors. That's what it says. Okay, so and that's, like I said, the desk does it. Okay, the walls do it. Okay, your bodies do it. Stars do it. Okay, an ice cube even does it, even though it's cold. Ice cube does it as well. Now, in this picture here, actually, it's a nice illustration of the concept of thermal radiation. So in this picture here, we have a traditional incandescent bulb. Okay, now a traditional incandescent bulb has a tungsten filament. It's one of the elements in the periodic table. A tungsten filament. How that works is you have a current that passes through this really, really, really super thin wire that's made of tungsten. And when the current passes through that, it has a very high resistance, and it causes the wire to heat up. All these electrons are flowing through it, causing these collisions, and it heats up a lot. Now, the filament itself is a really good example of this law because it's a solid object that gets extremely hot. And if you could look at an incandescent bulb through like a telescope and a spectrograph so you can see all the wavelengths, you would see a rainbow of colors. A light bulb produces a full range of colors, which is a good illustration as to why we are, why we are encouraged to not use these things anymore to light our homes and stuff. Okay, because if you think about it in terms of what we've been talking about today, this is actually a pretty barbaric way to light a room. Because what you're doing is you're passing a current through the filament here, and you're causing the filament to heat up and spew out all these wavelengths, some of which are put into visible light, and it lights the room up, and that's what you want. But some of the light, a lot of the light, is infrared light, okay? And you don't need any of that, right? What does the infrared light do? It just makes the light bulb hot and burns you. So it's a really simple way to light a room up, but it's kind of a barbaric way because it wastes tons of energy. Most of the energy of the light bulb goes into heat, not into lighting the room up. And so it wastes tons of energy. And so we're trying to use these CFLs instead. The lights in this particular room here, these fluorescent lights, most of those things work like CFLs, there's a gas. And you pass a current through the gas, and what it does is it causes line emission. Not continuous emission, line emission. So it's just particular wavelengths are being emitted. Like in these lights that are here, okay, you have mercury in these. And same thing with the CFLs, they're mostly mercury. And mercury has this nice property to it where it has emission lines at particular wavelengths that mimic sunlight. Okay, it's not sunlight, but it kind of looks like sunlight. And so it's a really cheap alternative to light the room up. Yes?
So that's why when you put a camera and you see those lines, it's because of that?
You bet. That's it. That's that. When you see the lines like that, you're seeing a diffraction going on, and you're seeing wavelengths separated, and the lines that you see are emission lines. There's some gas that's excited. Electrons are jumping to higher levels, are coming down, and they're producing those lines when they come back down. Yeah, absolutely. Okay, so anyway, this is a continuous emission spectrum. I like the light bulb example because it illustrates this law really nicely. And again, the objects don't have to be hot necessarily. They just have to have any kind of temperature. All right, the second law is on the concept of line absorption, okay, photon absorption. It says that light that comes from a thermal radiation spectrum, okay, passes through a cool low density gas, the result will be a line absorption spectrum, okay. So to illustrate this, we have our light bulb from the last example, but let's surround that light bulb with a gas. In this particular example, we'll do using hydrogen gas, okay, we're surrounding it with hydrogen gas. And if you attempt to look at the light bulb through the gas, what you will see is a rainbow of colors, like you see here, but there will be certain dark lines. And the dark lines are absorption lines, and they come from the gas picking out wavelengths of light that it happens to like, because it works with the electrons in the atom. And the result is this absorption spectrum. Okay? So you have to have a thermal radiation spectrum to begin with, and then when that thermal radiation spectrum passes through a gas of some kind, wavelengths get taken away. That's what line absorption is. Okay? The third one is on line emission. So it's the opposite process. So what it says is that if you have a low density gas that's already been excited, okay, like in the last example, okay, you already have these absorptions taking place, then eventually those electrons will have to de-excite, and when they do that, they have to release the wavelengths that they originally absorbed. And that produces line emission. Okay, so using the same examples here, what we're doing is we're taking our light bulb gas that surrounds it, but now we're going to take our telescope and we're not going to look at the light bulb. We're going to look at the gas, just the gas. And so if you do that, you will have a dark background because you're not looking at the light bulb anymore, so you won't see the rainbow of colors. You'll see a dark background, and every single place where there were dark lines before, now there's color. Because these are photons that were absorbed and now are being re-emitted by the gas. And that produces the line emission spectrum. Okay. And so everything we've talked about up to this point in Chapter 5 is all illustrated really nicely in Kirchhoffs Laws. Thermal radiation spectrum, line absorption, line emission. Okay. And this all obviously relates to stars, right? Because when it comes to a star, the surface of a star is the first law. The surface of the star is a hot, dense object, and it releases a thermal radiation spectrum that follows the laws of thermal radiation. Okay? Every single star has an atmosphere, and the light from the surface has to go through the atmosphere. And when it does that, wavelengths are going to be removed. That's when I showed you the spectrum of the sun last class. Rainbow of colors, and there's just thousands of lines, absorption lines, all over the place, because there's a lot of things going on in the atmosphere of the sun, all kinds of elements, different states, producing these absorptions. Okay, and that's the line absorption. Every single star is this: surface, thermal radiation spectrum, atmosphere, produces absorption lines. Now, the way you could talk about the third one, the line emission, is this. So, as I showed you in the example here, say we don't look at the light bulb, we just look at the gas that's around it. We should see line emission, right? Well, let me show you how that works. Okay, let's go look at well, I think it's here. All right, so I showed you this picture when we talked about the moon, but a solar eclipse is a good illustration of this third law. Okay, so for the solar eclipse, the moon passes in front of the sun. Okay, so we cannot see the photosphere. We cannot see the surface anymore. So it's like, it's like the third example of laws of radiation, of thermal radiation, because we don't see the light source. Okay, what you see, it's kind of hard to see it here, but if you look around the edges, we see these features, these atmospheric features. Okay, those are line emission. That's line emission. That specifically comes from hydrogen gas. The colors that you see, the pinkish color, is a mixture of the three lines of hydrogen that shows up in the visible part of the spectrum. So this is a great illustration of line emission, the third of Kirchhoffs laws. The moon blocks the surface, so we can't see the thermal radiation spectrum. We cannot see the absorption lines. We just see the atmosphere. And what we're seeing in the atmosphere is the emission of all these lines that were once absorbed from the surface. Okay. This is not common to see. I mean, we can do this for our sun. We can't really do this for other stars. It's actually very hard to see the emission lines of other stars. And we generally don't care about those because they don't have as much information as the other stuff does. So. All right, so those are the three laws that sums up the types of ways that light and matter interact. Okay, do you have any questions about those? Oh, okay. I don't know. I'm like thinking, why is this picture here? I don't know why I see it. Okay, so let me just give you a brief example of some of this stuff here. This is part of the Eagle Nebula. In fact, you've seen pictures like this before. I mean, one of the most famous pictures from Hubble is called the Pillars of Creation. It's from the Eagle Nebula. It's these three pillars that rise up. I'll show you that a bit later in the class. Not today, but this is just an aspect of the Eagle Nebula. What's going on in this image here is this is a Hubble image that's taken with a couple different filters. The red color that you see here is a filter that was specifically designed to capture line emission from hydrogen. Okay? And all the places where it's red is where hydrogen gas exists, and places where it is a bit brighter, obviously there's more of it. Okay? Now, what's going on in this pillar is there are stars being born in this pillar. Okay? We can't see them, though. They're embedded in the pillar. What happens is you usually have big clouds like this that are somehow triggered to collapse, and the stars are initially sort of embedded in these clouds. They're in these little like dust cocoons, basically. And it takes several millions of years for them to emerge out of the cocoons, basically. But before that happens, we want to know where they're forming. And we can't tell in the visual wavelength image. The reason we took the picture here in red for hydrogen is because we're trying to see all of the areas where there's a higher concentration of this gas. We're just trying to see the layout of the gas. Now, we also took an image in the ultraviolet to pick up emission lines from oxygen, okay? And the reason we're going to do that is because the stars that are starting to form here, okay, they're starting to get really hot. And they're producing a thermal radiation spectrum. And that thermal radiation spectrum is going to start flying into space. And if it encounters the interstellar medium, the gas and stuff, and all the dust that's around here, that gas is going to absorb some of those photons, and it's going to emit them. And so the blue color that's what all that is. The blue color is gas that is encountering the light from all these brand new stars. And it's causing the gas to be excited, and then it's emitting these emission lines. And we take this picture because we're looking for the place where the emission seems to be more prominent. And it's right here. This particular spot on the upper left here, where it's very bright, is where there is more of this emission taking place than anywhere else. And that means inside of that particular spot is where these new stars are formed. Okay? And so we generally take a picture like this to investigate the surrounding region, and then we usually follow this up. So what will happen is somebody will follow this up. They'll isolate this particular patch, and they'll use an infrared telescope. What an infrared telescope will do, an infrared telescope can look through the dust. You can look through it, and you can see what's going on inside of that. You don't want to do that for the whole region here. Okay, resolution on infrared telescopes are generally not as good as optical telescopes. You'll spend forever digging through this thing, but this UV emission from oxygen tells you exactly where to look up here. And so somebody will come through and they'll study the star formation happening here and how many stars are going to form. So anyway, it's a good example of how some of this stuff is used to sort of probe the region here and figure out what's going on. Okay. Okay, we've got one more topic before we finish up here. And it's called the Doppler effect. Okay. Now, everything we have discussed up to this point has a minor assumption to it. Okay, and the minor assumption is this, that the objects that we're interested in looking at, they don't move. Or if they do move, they don't move very fast. Okay. What the Doppler effect is light changing wavelengths as a result of objects moving. And in some cases, they can move very fast and it cause a huge change. Now, you've experienced the Doppler effect in another way, actually. So let me actually show you this first before we get into, and you do need to hear this. So the Doppler effect is something that happens with any kind of object that's a wave. It could be light, but sound is also a wave, and so it can happen with sound. Now, I'm showing you a video, but the actual video is not important. The sound is important. I just don't have a sound clip. I just have the video. So while you watch the video, it's okay. So what's happening in the video is somebody's just hanging out in the corner here. They're taking a video of this fire engine going by, right? And so what you want to focus on is the sound that the fire engine makes as it approaches you. And then what happens is it's going to pass the person and start to move the other way. Focus on the sound. Okay, so there's a pitch change there. Okay, that's Doppler effect. Okay, if that fire engine was standing still, you would hear the siren at a particular pitch. When it's moving towards you, it's a different sound. When it moves away from you, it's a different sound. Now, you really hear it as soon as the fire engine passes you because it goes from a higher pitch to a lower pitch. Okay, that's a wave-like phenomenon that's happening here, and it's due to the fact that it moves. Okay, that's the Doppler effect. Happens for sound, happens for light as well. Okay. So let's talk about it. In this example here, we got a fire engine, okay, flying to the left here. Now, that fire engine has a particular frequency, particular pitch to that sound. For the person that it's approaching, what happens is the fire engine is moving in the direction that it's emitting the sound. What that does is it compresses the sound waves, and it effectively creates a smaller wavelength and therefore a higher frequency. So the sound that you hear is a higher pitch. You hear a higher frequency sound because the waves are being compressed. Okay? When the fire engine passes you and it's moving away from you, then the fire engine is now moving in the opposite direction that it's emitting sound, and what that acts to do, it acts to stretch the waves out. It creates a longer wavelength and therefore a lower frequency, so it's a lower pitch. Okay, that's what's happening in this example here. We call the approach a blue shift, and we call the recession or the moving away from you a red shift. Okay, the same thing occurs with light. If there is a star that is, say, approaching you, or any kind of light source at all, this primarily works for stars, if the source is approaching you, what it will do is it will compress those light waves, and it will produce a shorter wavelength than what it would do if it was not moving. And so that creates a smaller wavelength, and we call that a blue shift. Now, the reason why you call it a blue shift, though, is because it's not because the light turns blue. Okay, this picture is a little deceptive because they show blue here. Yet I'm not trying to tell you that the light turns into blue. I mean, it could turn into blue. What happens is the light becomes a shorter wavelength. Okay, so if it's red, it could turn into yellow. If it's yellow, it could turn into green. If it's blue, it could turn into ultraviolet light. So it's not necessarily blue. We just call it blue because blue is a shorter wavelength than the other visual wavelengths. So we just refer to it as blue shift. But what you should associate with blue shift is shorter wavelength because the object is moving toward you. Okay, moving toward you. Red shift is what occurs when an object moves away from you. And what that does is it acts to stretch the light out, and it creates a longer wavelength than normal. So it's a shift to longer wavelengths. We call that a red shift. Again, the light's not red, but it will produce a wavelength of light that's longer. Okay? So, as I've mentioned before, like my laser light here, okay? My laser light is red. And the laser light is very similar to the Balmer alpha emission line for hydrogen. The Balmer emission line for hydrogen is 656.3 nanometers, okay? That's what this is basically producing when it's at rest. But if there was a red light, this red light, that was approaching you very rapidly, this wavelength, you would detect it as a shorter wavelength. You might detect it as 654 or something, 653. If it was moving away from you, you would detect a longer wavelength. Okay, so we expect this wavelength. But when objects move, it shifts, it changes. And that's one of the ways we're able to detect motion for objects. Okay, so we may know that a particular star has hydrogen absorption lines. It could happen with absorption or emission. But if we detect changes in the wavelengths, and they're all equally different, then it's due to motion or something like that. And the way we calculate this is a real simple equation. Okay. Now, I'm not really going to have you do much with this equation, but I do want you to understand it. So explain what the equation means. The equation is a proportion. Okay. The left side of the equation is a lambda, delta lambda, which delta lambda means the difference in the wavelength. Okay, from what it's supposed to be to what you detect it to be. So there's some shift that occurs, divided by what the wavelength would be if it didn't move at all. Okay, and that equals a ratio of velocity to speed of light. Okay, so if you can detect how different the wavelength is from what it's supposed to be, then you can work out how fast it moves, whether it's toward you or away from you. This only works for what we call radial velocity. Radial velocity means motion that's toward you or away from you, not side-to-side motion. You cannot do this for side-to-side motion. Only motion that's away from you or toward you. Okay, that's why for the fire engine, okay, it was moving towards then away. Okay, but if you're looking at a fire engine that's moving, you just say side to side at a faraway distance, you're not really going to tell much of a difference there. It's got to really move toward you or away from you. So let me give you some examples of this. Okay, so in this example here, we're looking at a particular star. This red line that you see, this is what we call the rest or laboratory wavelength. This is the Balmer line of hydrogen, 656.3 nanometers. That's exactly what it is, 656.3 nanometers. That's what we expect that hydrogen line to be if we didn't move or Arcturus, the star, didn't move. Okay. Now, one of the ways we detect our motion in the solar system is by staring at faraway stars, and we look for lines shifting back and forth, indicating that we are flying around the sun. And that's what's actually being observed in this picture here. So at the moment that the top spectrum was taken, we happened to be moving toward Arcturus, or Arcturus is moving towards us. I mean, we're moving towards each other. And what's happening here is there is a small shift in the wavelength. It's not where we expect it to be. It's slightly shorter. This is blue shifted. This wavelength down here is red shifted. It's a slightly longer wavelength than what we expect. Okay. Now, for a single line, it may not mean a lot, but when you see a pattern of lines, say the pattern of line that corresponds to some element, if they're all equally shifted, then we know it's due to Doppler effect, and we can calculate how fast the object is moving, us or them or whatever it is. Okay. So that's one of the ways we detect it. Okay. Another way we can detect this stuff is through rotation, because rotation is a type of motion as well. So we actually can determine how fast things rotate by the appearance of their lines as well. Okay, so in this particular image here, and I really hate this image, and I mean to change it, because the colors that you see in the emission line here, just ignore them. Okay, red and blue, just ignore them. It's really awful. Anyway, the blue emission line here would be what the emission line would look like if the object wasn't really spinning at all. Okay. The red that you see here is what the line looks like once you allow the object to spin. Okay. So what's going on here is this. If we are looking, for example, at a star, okay, so say Earth is down here and we're looking up at the star. If a star spins, what happens is one side of it is moving away from us and the other side is moving towards us. So the object itself is not, uniformly shifted, but parts of it are shifted. Okay? The right side is red shifted because it's rotating away from us, and the left side is blue shifted because it's moving towards us. And so in the spectrum here, what happens is the emission or the absorption line becomes broadened. We call it Doppler broadening. It becomes thicker. And the reason it becomes thicker is because there's an extra amount of light at the wings, at the bottom here, that are due to the rotation of the object. And so for certain objects that rotate very, very fast, this becomes extreme, and all the absorption or emission lines get very, very fat, very, very broadened. And we can measure how broad that is, and we can actually calculate how fast it spins. And so that's another example of this Doppler effect. Now, this is not translational motion. This is spinning completely. And what it does is it takes any absorption or emission line and just broadens it, makes it bigger. And so that's an effect as well. All right, so one question to wrap it up here. In theory, if you travel fast enough in your car toward a street light, which of the following could you achieve? Okay, think about that for a moment. All right, real high. Got lots and lots of people saying A, and A is good. All right, so let me say a couple things about that, though. Okay, so you are moving toward the light, right? So you expect a blue shift. That means whatever the wavelength is to begin with, you should expect it at a shorter wavelength. So it was red to begin with, and a shorter wavelength would be green. So A is good, okay? B is not so good, right? Because B would be a red shift, okay? Now, a good question to ask is this. Is this an argument in court, right? I mean, because you're making a red light turn green, right? So the question is, well, let me think about this. Can I get away with this, right? Well, let's actually use the equation that I wrote here, okay? So red light is approximately, the wavelength of red light is approximately 650 nanometers. Okay? Now, green light is approximately 550 nanometers. Okay? That's the difference between those two wavelengths of light. So the red wavelength is what it is if you're not moving, and somehow you move so fast that you blue shifted the light, and now it becomes 550 nanometers. Okay, well, let's put it through the equation and see what we get. Delta lambda is the difference between the two. The difference between these two numbers is 100. That's the delta lambda. Okay, the lambda naught, the wavelength of the rest wavelength, would be the red light, so 650 nanometers. Okay, now that's equal to the velocity over the speed of light. Okay, this ratio here, 100 to 650, that's very close to 1/6. Okay, that means you would have to be traveling at 1/6 the speed of light. So it's not an argument you could use in court, because you would be admitting to some pretty horrendous speeding. Right? So you couldn't. So this is not a reasonable thing to do. But if somehow you could manage to travel at 1/6 the speed of light, then red lights would turn green. They would. Okay. Yeah. So now the example I showed you with Arcturus, that shift was like tenths of a nanometer. And tenths of a nanometer turned out to be kilometers per second, which is like, the speed at which something like the Earth moves. All right, now let me ask you one follow-up question. This is kind of an interesting question. Say you did this, right? You're going 1/6 the speed of light. The red light now looks green to you, but you notice the green's on top, so you're not too confused by that. Anyway, you blow through the light. Okay, you look behind you at the signal from the other side, and what do you see? What do you think you see when you look behind you? Red. You would not see red. You would not see green. What would you see? Not red, not green. Think about it. You were the light was blue shifted when you approached it. Now you're moving away from it, right? What? Not yellow. Give you a hint. It's not a color. What'd you say? You said nothing, right? That's correct. You would see nothing. You would look behind you, and you wouldn't see the light at all, right? Because what happens when you redshift red light? What does it become? It becomes infrared light. And you can't see infrared light. So you blow through the light, you look behind you, and you don't see anything. You think the light signal is broken, but it's not. It's been redshifted to infrared light, and you can't see infrared light. So yeah, that's what happens. So you go from blue shift to red shift, and the light is now past red into the infrared. You can't see it. So that's what happens the other way. All right. We're done.